On behalf of Harishchandra Mathematics Society, we welcome you all to the Harishchandra lecture series by Professor Mahen Mj of School of Mathematics, Tata Institute of Fundamental Research. Please give a big round of applause for Mahen Mj. We are thankful to our acting principal, Dr. Hemchand Jain sir, who spared his valuable time to be present over here. Now I request our honorable acting principal to say a few words.
Professor Mahen Mj जी, डॉक्टर रत्नेश जी और मैथमेटिक्स डिपार्टमेंट के सभी शिक्षकगण, संजय पंत जी, dear students who have come all the way from different part of the country to for this function. In this college, in 1994, we started the Harishchandra Mathematics Society, and that was the year in which the college got the mathematics honors for the first time. And since then, this Harishchandra Mathematics Society is doing a wonderful job. And from 2010, the college is holding Harishchandra lecture series, and we have invited eminent speakers on this occasion. And today we are fortunate to have Professor Mahen Mj ji, who is a professor in the School of Mathematics, Tata Institute of Fundamental Research. And his guidance will help all our students who are actively involved in doing the research in the field of mathematics. Without wasting any time, I will request Professor Mahen Mj ji to take charge of this lecture series, and on behalf of the college, I formally invite you to take charge of this. Thank you.
Thank you, sir, for your valuable words. Okay. Now I request Professor Mahen Mj to begin with his talk.
Hello.
All right. So thanks very much for this invitation. And yeah, it's a great place to be to visit. And So the title of the talk is what is hyperbolic geometry, and we'll come to the topic of the talk as a little far into the talk. Am I audible at the back?
Yes, sir.
Okay. All right. So before coming to hyperbolic geometry per se, let's start with the place where we start learning geometry, which is Euclidean geometry in school. Yeah. Yeah. So then that's really our sort of first formal introduction to axiomatic or formal mathematical reasoning, where there's a bunch of axioms which are given, which define, so to speak, the playing field. And then once you have those axioms in hand, you start deriving properties of various objects. So it's a procedure by which we extract the basic minimum, that's the finite small set of axioms of geometry, and then we start deriving properties of geometric objects. So this exercise was done by Euclid a while back, around 200 BC, and that's what formulates for us the basic axioms of plane or Euclidean geometry. And we take as the guiding principles of Euclidean geometry some very small number of axioms, 4 of them to be precise, and I'll just say what these are to start off with. Okay? The first Euclidean axiom says that if you have any 2 points in the plane, you can join them by a unique straight line. Okay? So that's So the first axiom sort of defines for you a straight line segment. Yeah? When we draw straight lines in school geometry, what we are really drawing are finite straight lines. So which means they have endpoints, and once you have endpoints, you have a segment that joins them. So that's what's called a straight line typically. But we shall refine this notion a little and call it a straight line segment rather than a straight line. Okay? The second axiom says that once you have a straight line segment, it can be extended infinitely in both directions. So so the first axiom defines for you a straight line segment. The second axiom defines for you a straight line, which means a bi-infinite straight line, and a straight line which extends infinitely in both directions. The third axiom defines for you a circle, which basically says, how do you define a circle? It's the locus of points which are at a fixed distance from another fixed point. Yeah? So that's a defining property of a circle. And then the next axiom defines a right angle. Basically it says that all right angles are equal to one another. What does that mean? Okay. So before I come to the fifth axiom, which is not quite, it's not on this slide, but that's going to be really at the heart of this talk. I want to sort of emphasize something about these axioms. So these axioms are defining for you the basic players in the game of Euclidean geometry. Okay? So the first axiom essentially tells you 2 points define for you a straight line segment. Yeah? Once you're given 2 points, that defines for you a line which is a straight line segment. And the second axiom says a straight line segment defines for you a bi-infinite straight line. Yeah? So if you're given any straight line segment, there's a unique way of extending it infinitely in both directions, and that gives you a bi-infinite straight line. The third axiom defines a circle, and the fourth axiom I would like to say is something that defines for you a right angle. So where is it all coming from? It's really coming from, you start off with a point. Yeah? So that's the basic undefined concept. Okay? A point on the plane. Once you have 2 of these points, so the basic minimum that you start off with is points in space or points in a plane. Once you're given 2 of these, from that you extract a straight line segment. From the straight line segment you extract the bi-infinite straight line. from a point and a measure, that means a distance, you extract a circle. How do you extract a right angle from a straight line? Yeah? So basically, so if you have a straight line which goes from, say, minus infinity to infinity, and you pick a point on that straight line at random, yeah, just pick any point there, then the angle from minus infinity to infinity is bisected by some line, and that half that angle, I mean, after you bisect that angle from minus infinity to infinity at some point, yeah, the angle that you get is called a right angle. Okay? So why is it called a right angle? Because all other angles are wrong angles. Okay? So that's sort of the, I mean, so it's some basic notion that comes up, and it's the first angle that you would be thinking of naturally. Okay? So it's defined in terms of two things. One, a bi-infinite straight line. Two, a point on that bi-infinite straight line. Okay? So this third axiom, when it says that all right angles are equal, what it's really saying is that this angle that you get by bisecting minus infinity to infinity at some point is independent of the choice of the bi-infinite straight line, and is also independent of the point on the bi-infinite straight line that you chose. Okay? That's the meaning of all right angles are equal. Yeah? Okay? So essentially, again, going back, you can really start off everything with, if you have a notion of a point on a plane, all these things follow. Yeah? If you have a point, you have 2 points. 2 points means you have a straight line, a straight line segment. Straight line segment implies bi-infinite straight line. A point and a distance means a circle, and a straight line gives you a right angle. Okay? So these four are sort of basic players of the game, which are extracted from the notion of the plane and a point on it. That's it. Okay, so these are the basic players. Now we come to the fifth postulate. This is not called an axiom, but it's a postulate. It's what's called the parallel postulate. It basically says that if you have two straight lines, yeah, two bi-infinite straight lines which fall on a third straight line, yeah, and so suppose you have two straight lines coming. I mean, so imagine my hand is a transversal, and you have two straight lines intersecting it, and on one side the sum of the interior angles is less than 180 degrees, less than pi. Then if you extend these two guys, they are going to go and meet and form a triangle. Okay? So if the angle on the left side of the transversal is less than 180 degrees, it's going to meet on the left. If the two lines make an angle less than 180 degrees on the right, they'll meet on the right. Okay, fine. Well, what if they fail to do either? Yeah. So then there will be parallel lines. Yeah, that's right. So they don't know whether to meet on the left or the right, so they don't meet at all. Okay? So two lines which do not meet at all are called parallel lines. That's all. It's a definition given to two straight lines which do not meet at all. Okay? And then the defining property of that is that the angle that they make on any transversal, the sum of the interior angle that they make on any transversal is exactly equal to 180 degrees. Okay. So these are the Euclid's axioms. And Euclid essentially, I mean, the fifth axiom is not called an axiom. Even in Euclidean geometry, it's not called an axiom. It's called a postulate. Yeah. So there's a difference in status between axioms and postulates. Axioms are things that obviously should be true if you want to get anything meaningful out of it. Yeah? A postulate does not have that kind of a confirmed or sacrosanct status. Yeah? It's something about which people have doubt. Yeah, in the sense that you could possibly change that postulate and get something meaningful also. Euclid's thinking was that this fifth postulate, the parallel line postulate, also called the parallel postulate, that should be something you would be able to derive from the rest of the axioms. Yeah? This was essentially Euclid's thinking, and the problem he posed was, can you derive this fifth postulate from the remaining four axioms? Okay? So this is the problem. The problem we are going to address during this talk, it's a 2,200-year-old problem. Basically asks you, can you derive the fifth postulate from the remaining axioms of Euclidean geometry? This problem has been solved, okay? Any guesses how long it took to solve the problem? I mean, for those who have not seen this before, I mean, only those, so please don't tell me the answer if you know it from something that you've read on Wikipedia or on the internet. But if you just take a guess as to how long it took to solve this problem. 1,000 years, okay, first guess, 1,000 years. Huh? 2,000 years. 2,000 years is pretty close. Okay, so we'll get to it. The thing is, the point of this is not to say, I mean, it's a hard problem, took a long time to solve. Actually, what we'll try to investigate today is it really took a little more than 2,000 years, marginally more than 2,000 years. But the real answer that we will like to put forward is why it took so long. Yeah. There's something fundamentally, I mean, there was something that's a conceptually deep behind this question which was not known to Euclid, yeah? Which was not known to many people for at least 1,500 or 1,600 plus years. People just did not know, and so the conceptual foundation of this is not visible here. And to excavate that conceptual foundation took a very long time. Okay. So before we get to the problem, we will say that the parallel postulate was formulated in a different way. The fifth postulate, or the parallel postulate, is equivalent to the following statement. This is called the Playfair's axiom or the parallel line axiom, which essentially says that given a straight line and a point outside that straight line, there is exactly one. There's one and only one straight line through that point parallel to the first line. Yeah? So the fifth postulate is equivalent to this. Through a point, not on a straight line, there is one and only one straight line through the point parallel to the given straight line. So this is an equivalent formulation of the fifth postulate, and the attempt to prove the fifth postulate from the remaining four axioms is exactly, it's that process which gave rise to what we now call hyperbolic geometry. Okay? So what is hyperbolic geometry? It's a theory that came up by attempting to answer this very old question. Alright, before we get to the answer, just a little bit of history. So, fast forward 2,000 years, Gauss started thinking about these parallel lines in the late 18th century, and he essentially solved the problem in the early 19th century. In a letter to a friend called Taurinus, he wrote that the assumption that the sum of the three angles of a triangle is smaller than two right angles leads to a geometry which is quite different from Euclidean geometry, but which is itself completely consistent. So this parallel postulate, there's a third way of formulating it, which is that the sum of the angles of a triangle is exactly equal to 180 degrees. Okay? So there are these various things. There is the first one axiom that we stated there. Then there is this parallel postulate through a straight line and a point outside it. There is a unique line parallel to the first guy. Or sum of the angles of a triangle is equal to 180 degrees. All these three are equivalent. In fact, in school geometry, you derive one from the other, and you can go the other way. You can derive the parallel postulate from sum of the angles of a triangle is 180 degrees. Yeah? So these are different ways. So what Gauss is essentially saying here is that you can have a geometry where the sum of the angles of the triangle is not equal to 180 degrees, it's less than 180 degrees. Yeah? Which means that he is formulating a geometry where the remaining four axioms are satisfied, but the fifth axiom is violated. Right? The fifth axiom, replace it by sum of the angles of a triangle is equal to 180 degrees. Yeah? What Gauss is saying, no, I'll have a fifth axiom, sum of the angles of a triangle is strictly less than 180 degrees. Yeah? And even then, the geometry is itself completely consistent. Completely consistent means that the remaining 4 axioms are satisfied. You do get a genuine. So the first 4 axioms is, in this particular sense, what is defining for us a geometry. Okay? So what is the resolution then? We'll see how this problem gets resolved. But once you have this answer, what do you get? Euclid posed the problem, derive the 5th postulate from the remaining 4 axioms. Gauss, what does Gauss's answer tell you? It basically says that you cannot derive the 5th postulate from the first 4 axioms. Does not mean it's false. Yeah? Euclidean geometry is an example where the first 4 axioms hold and the sum of the angles are equal to 180 degrees. Gauss says there's a different geometry where the first 4 axioms hold, but the 5th axiom is violated, which means neither the 5th axiom nor the negation of the 5th axiom can be deduced from the first 4 axioms, which means that the status of the 5th axiom is independent of the first 4 axioms. Okay? This is a certain fundamental logical point that Gauss is making here. Yeah? And essentially this is not just a feature of Euclidean geometry, it is a certain fundamental feature of any sophisticated system of logic. Yeah? The deepest theorem in mathematical logic in the 20th century, perhaps ever, something called Gödel's incompleteness theorem, essentially says that given any finite second order logical system, there will be statements in that system which are neither provable, which can neither be proved nor disproved. Okay? Which means neither the statement nor its negation can be proved using the set of axioms that you already have. Example here, if you take a logical system defined by the first 4 axioms, then the 5th guy, sum of the angles is equal to 180 degrees, cannot be proved. Sum of the angles is not equal to 180 degrees, cannot be proved. Okay? So that's an example of a statement such that neither the statement nor its negation can be proven using the other 4 axioms. Okay? So this is an example of incompleteness, which means there will be statements which neither the statement nor its negation can be proved within the axiomatic system. Okay? So there's something, I mean, even in terms of our fundamental logical structure of what we use to do mathematics is really being brought up here. Okay? Fair enough. Now we come to a little bit of gossip. Gauss did not publish this work. Okay? In the 18th, okay, so a little bit before, in the 18th century, what you call hyperbolic sines and hyperbolic cosines today, basically e to the x plus e to the minus x by 2, that's called the cosine hyperbolic function, right? E to the x minus e to the minus x by 2, it's called the sine hyperbolic function. Those functions, why are they called hyperbolic sines, hyperbolic cosines? It's because those turn out to be the right functions to look at to define sine and cosine in hyperbolic geometry. That's why they are called hyperbolic sine, hyperbolic cosine. Okay? And these functions, the analytic part of the theory, or the trigonometric part of the theory, these were brought out by Lambert in the 18th century. 19th century, after Gauss, 1824 was Gauss, but 2 mathematicians, Hungarian mathematician called Bolyai and a Russian mathematician called Lobachevsky, these are the 2 people who really wrote down the stuff and discovered hyperbolic geometry independently. Basically, that statement that Gauss has made there, these are the 2 guys who wrote it up independently. It is also called the Lobachevsky claim. Okay? So this was in the 19th century. More precisely, 1829-30 is when Bolyai published his work. It's called On the Principles of Geometry. And The absolute science of space was, on principles of geometry was brought out by Lobachevsky, it was in Russian, and Bolyai called his stuff the absolute science of space. The term hyperbolic geometry for this came much later, came another 40 years later, by somebody called Felix Klein, 1871. Incidentally, one story. So the first International Mathematical Congress was held in 1893, and Felix Klein was, this guy who called this stuff hyperbolic geometry, a young man who, well, relatively, he was the president of that session, the chair of that session. And he encouraged people to, so this was held in Chicago in 1893, and Klein essentially, this is August of, under something called the Columbian Exposition, so there was an International Mathematical Congress, and Felix Klein essentially asked for mathematicians and scientists to let their science cut across political boundaries. Okay? So essentially that science is not conditioned by any kind of particular society or country or anything of that. That's all. It was something that was, it's a certain fundamental value that most scientists today subscribe to. That was explicitly stated at the first International Mathematical Congress in 1890. Okay. So now let's get back to the maths. I'll restate now the parallel postulate in the form in which we prove or disprove things today. Okay. So given a straight line, and now we'll actually excavate and put some of the hypothesis that was already assumed in Euclid, but out in the open, sort of explicitly. See, these are hidden assumptions that we often make while doing some parts of mathematics. And part of the problem in solving this problem that Euclid posed was that the hidden assumption was not there in the open, so that the point of attack was not known. So what is it? It's an obvious statement given a straight line in a plane P. So something that Euclid and those who worked around that time took as obvious. Yeah? And okay, we are all doing plane geometry. What's the point in stating it explicitly? The whole point of this exercise is that it's required to state it explicitly so that we understand where exactly the problem lies. Yeah? So given a straight line in a plane P and a point x on the plane P lying outside L, there exists a unique straight line L prime lying on the plane P, passing through x and parallel to L. This is a parallel postulate. The plane P is important. So assume that you have some, so for example, a simple thing is that we are not talking about space. Yeah. So if you have a straight line lying on the floor of this dais, yeah, and you have a point outside it, then you can take a line in the plane parallel to that and rotate it. Yeah? You're going to get infinitely many lines at any angle parallel to the given line through a point outside it in space. So we are talking about plane geometry and it needs to be made explicit. Yeah? All right. So the problem in this statement is that prove this postulate from the other axiom, the Hyperbolic geometry. So this is restating the whole problem. Very good. The basic point is what people did not inquire is what is this underlying assumption? What does it mean to say? I mean, it was assumed and not made explicit, not inquired into. What does in a plane P mean? Yeah? What is a more fundamental explanation of being on a plane P? This is the fundamental question that we should be asking. So the question really is, what is a plane P? Once you have a notion of a plane P, can you extract from it the notion of a straight line? Once you have a notion of a straight line, the notion of parallelism is okay. Once you have a notion of a straight line, two lines are parallel and they don't meet. That's it. Yeah? So the notion of parallelism can be extracted once you have a notion of a straight line. But can you have a notion of a more fundamental notion of a plane P, which was not explicit, not, I mean, people went around with this sort of common sense, so-called common sense idea of a plane P, meaning geometry that we do on a piece of paper is plane geometry. Yeah. That's not a definition, that's not a mathematical definition. The underlying structure has not been revealed. Yeah? And we somehow say that, okay, underlying structure not being revealed means, okay, that means it's obvious. It's far from obvious. Okay? So really, it's trying to excavate and understand what this underlying structure is that gives rise to the real solution to this problem. Okay? Fair enough. So once you have a notion of a plane P, then we'll come to a notion of a straight line. So this is really the point. I mean, a large part of the problem was because people did not investigate what the underlying assumptions were behind the axioms, what was the substructure on which the axioms were imposed, and what kind of an answer are we seeking about a plane P. And here's the next answer. This answer you get in high school, in class 11, class 12. The Euclidean plane is R2, equipped with a way of measuring distances. And you've seen this formula in many places, ds square equal to dx square plus dy square. What does it mean? This is an infinitesimal form of the Pythagoras theorem, right? A square plus b square equal to c square. For a, b, the sides of a right angle triangle, c, the hypotenuse. Yeah? If you put it in infinitesimal form, you get exactly this. Well, what does infinitesimal form really mean? Yeah? What is that? I mean, this is just a bunch of symbols, right? If you showed it to a Martian would have no understanding of what these symbols mean. ds, is it a number? What is it? So there is some concept behind it. Yeah? So before I explain what this means, how many years have we come so far? We've said that this is what I've answered the first part of the question. What is a plane P? Yeah? How many years have we come from 200 BC to get this?
2015.
No, this is 2015. When do you get this formula? Where do you get? Who came? Whose idea was this? Pythagoras knew what ds square equal to dx square plus dy square is. Pythagoras was 200 BC, around the same time as Euclid. So this is something that you learn in school, but you sort of do not realize that there is something incredible going on. How would you make sense of this? ds square equal to dx square plus dy square. What is going on? What's the mathematics there? Did you know it in school? Do you have it in algebra? Do you have it in geometry? Do you have it in trigonometry? What subject is it? Calculus. So who came up with calculus? Yeah, so it's 16th century, right? 16th century already we have, so the point is, in order to even define what a plane P is, the stuff that Euclid never bothered about, yeah? So this fundamental question, in order to get a satisfactory answer, it took us something like 1800 years, yeah? So we've already covered a huge amount of those 2000 years. So basically we learn it today in high school, class 11, class 12, yeah? And we generally, okay, so there's some rules, you manipulate, you write limit, some x goes to the other, and then if you have something at the top, something at the bottom, you cancel them off, you get some answer, you get some mark. But the wonder of it, I mean, why it is, say, this is a concrete example where it took us something, mathematicians took all human beings doing mathematics or science, some 18, at that point of time there was no division, it was called natural philosophy, yeah? Physics, chemistry, mathematics, I mean, people were able to do all of that together by Newton's time, yeah? So so it took a huge amount of the finest minds from nearly 2000 years to come up with, it was so deeply hidden, yeah? The structure behind the plane P, which was thought of as, quote, obvious, or those who are more honest would tell you, we don't have the faintest clue what the plane P means, yeah? But we can work with it. So the more fundamental answer was given essentially post-Newton. So what does this formula really mean? It tells you a way of measuring lengths. Yeah? This formula in itself is completely meaningless, but it packages a huge amount of information. It tells you a way of computing lengths of arbitrary curves, not just straight lines. Pythagoras only tells you lengths of straight lines. If you have coordinates, Descartes for example, it will be square root x square plus square root y square. That's some way of telling you lengths of straight lines. Yeah? Here, the infinitesimal form tells you arbitrary smooth curves where lengths can be computed. How? So suppose you have a smooth curve which is given by a parametrization. Yeah? X of t, y of t. Yeah? So you have some parametrization of a smooth curve. X coordinate is parameterized in terms of time t, y is parameterized in terms of time t. Yeah? Then the length of the curve is integral of that elemental length ds. What is ds? So if you ds is equal to dx dt, so it's ds is equal to square root dx square plus square root dx square plus dy square, right, from that formula. What does that mean? Parameterize it. So you take dx dt squared, then dt squared, right? dy dt squared. Once you take the square root, it just becomes dx dt square plus dy dt square root dt. And then there's an integral. Okay? So you have differentiation and integration coming in. Yeah? So what that formula really means is, it's a huge amount of information, not for just straight lines, but for every smooth curve, you now have a way of computing lengths. Yeah? That's what this formula gives. So it's much more than what people could remotely conceive of before calculus came into being. Yeah? By the way, calculus was discovered by Leibniz and Newton independently. Alright. So this is what this formula is. It's a way of measuring lengths of arbitrary curves on the plane. So R2 is the underlying space, equipped with a method of computing lengths, is what we call the Euclidean plane P. That's the definition. Okay? So this is the underlying structure which was not there before calculus came into being. Fair enough? So now what is a straight line? A straight line in this notion, yeah? A straight line in this context, once you have given R2 with this way of measuring distances, what distinguishes the straight line? Yes? Is the shortest path, right? So, given 2 points, the straight line is the unique path that realizes the shortest distance as per that formula. Yeah? So now a straight line is not something that you have to define and as a player in the game as in Euclidean geometry. Right? It starts out, once you have a way of measuring distances, paths that give you the shortest distance automatically pop up. And those turn out to coincide with exactly what we knew as straight line segments in Euclidean geometry before. Okay? So it's a concept that's emergent. Yeah? Once you have R2 with this way of measuring distances, ds square equal to dx square plus dy square, a straight line is begging to be defined. Yeah? It's defined as the shortest path between points. Fair enough. And parallelism, as I said before, is automatic. Two straight lines are parallel if they do not meet. Fine. Now, once you have this way of measuring distances, ds square equal to dx square plus dy square, you can think of it in terms of Euclidean geometry, you can think of it in terms of Cartesian geometry also, right? So then, the straight lines, the equations can be written down, y equal to mx plus c, stuff again that you learn in 11 and 12. Yeah? So if you have y equal to mx plus c, then through a point parallel to another, so through a point say x1 comma y1, how many lines are there which are parallel to y equal to mx plus c? Huh? Parallel. So given say x1 comma y1, and you have y equal to mx plus c. What does it mean for a line to be parallel to a line with slope m? The slope must be m. So how many lines are there through x1 comma y1 with slope m? 1. Y minus y1 by x minus x1 equal to m. That's it. So which means what? Once you have Euclidean geometry defined as R2 with this way of measuring distances ds square equal to dx square plus dy square, you have immediately one and only one straight line parallel to another line through any point, right? So, if you define, so the question is therefore, if you define a Euclidean plane to be something equipped with this ds square equal to square root dx square plus dy square, then the fifth postulate follows. Yeah? But I was saying that all this stuff about Gauss having said that there's a consistent system of geometry, but we seem to have proven the fifth postulate. What has gone wrong? So once you have the plane equal to ds given by ds square equal to dx square plus dy square, you don't have a choice. The fifth postulate also emerges. Yeah? Then where's the problem? So have we actually proven what was the original problem? From the four axioms derive this. Have we done that? No. We have defined something ds square equal to dx square plus dy square in which those four axioms hold. And in that particular definition, the fifth postulate also holds. Right? So what do we need to do? We need to change the definition of R2 with ds square equal to dx square plus dy square such that the first four axioms hold and the fifth postulate. So the point of attack really is that little innocent looking formula. So what do we have to do? We have to change this formula ds square equal to dx square plus dy square. Yeah? Making sure that lengths are still positive. Okay? Making sure that the first four axioms hold. So we want a more general geometry. So take some open subset of R2 and now instead of dx square plus dy square, there is another hidden assumption which is again because it's quote unquote obvious, it's not written down. Dx square is 1 times dx square. Dy square is 1 times dy square. But 1 is not the constant 1. 1 is actually the constant function 1 on the entire plane. Yeah? So what we have not written down, its understanding is important. Yeah? So we have written down this ds square now equal to some function now. F of xy is a positive function f of xy, dx square, another positive function g of xy, dy square, and f and g are positive. Okay? F and g could be 1 constant, in which case we get back our Euclidean geometry. Okay? So, in order to do something else, what do we have to do? We have to choose functions f and g carefully. Yeah? So, question is, therefore, the problem really boils down to, can you choose this u contained in R2 and f comma g such that the first four axioms hold and the fifth postulate is violated? Okay? So now we have a well-defined question which will take much longer, much less time to solve. It took a couple of 100 years to solve this problem. Okay? Choose the functions appropriately. Okay? So ds square equal to fxy. So f and g have to be chosen. What does this formula mean? Again, it gives you a different way of computing lengths. Yeah? Computation of ds becomes f of x t y t, again dx dt square, plus g of x t y t dy dt square dt. See, ds is now going to be equal to square root, not dx dt square plus dy dt square dt. Yeah? But there's an f of x t y t, there's a g of x t y t also. Yeah? So, this is a new way of computing. This is giving you a new geometry. Okay? Fair enough. And the shortest path in this general thing, this has got a name. The shortest path was the straight line, but in this general geometry we don't want to keep using straight line. So it's got a new name, it's called a geodesic. Okay? The shortest path realizing this thing is called the geodesic. So the geodesic between 2 points is the unique path that, so for example, so in the infinitesimal form, what is it? Suppose you have I of xy equal to x1, y1. Yeah? That's a map from the plane to itself. What does it say? that in the infinitesimal form, fxy dx square plus dy square, dx square plus gxy dy square is now equal to f of x1 y1 dx1 square plus g of x1 y1 dy1 square. Which means what? Infinitesimally, lengths are not being changed. Yeah? So that means the integrand in the computation of length is not changing. If the integrand does not change, then integral of 0 to 1, some function is not going to change. So if you have some arbitrary path, yeah, and now you hit it by an isometry, the length of that path does not change. Yeah? Which means that the shortest distances between 2 points also does not change. Which means geodesics don't change. So geodesics go to geodesics. Okay? Alright? So this is the basic point. Now we'll do, this is the only point in this talk where we'll do a bit of a rabbit out of a hat. Yeah? So, what is the problem now? The earlier problem was we had no idea of what a plane P was. Yeah? Took us 1800 years to excavate and find out the underlying structure. So this is something that's called energy intensive. You have to dig very hard into the surface structure in order to get something underlying. Yeah? Now what do we have? Now we have this whole collection of functions f and g. What do we have to do? We have to choose f and choose g carefully. Yeah? From out of what? From the space of all positive functions. So the first thing was we had no idea. Now we have too much. Yeah? We have to choose one out of these things carefully. Yeah? So it's in physics terminology, the first one is energy intensive. The second thing is to minimize entropy. Yeah? So minimize disorder. You choose the one that you expect that will give you the most ordered solution. Yeah? Give you exactly, so basically instead of having, so now you have no idea which direction to go. You know that this is a plane, yeah? But you have no idea which direction to go. But all these directions are available to you. So you have to choose a direction carefully from infinitely many directions that are available. Yeah? So which direction it is? Here is the bit of a rabbit out of a hat. I'll say a little bit about it, but not enough. So the open subset of R2 that we look at is the upper half plane. Yeah? X, y greater than 0. And the metric we put on it is f of xy equal to g of xy equal to 1 by y square. How do we make this choice? This is a completely different story, a different 1 hour talk. Okay? Roughly, actually the solution that I am giving you today is not Lobachevsky or Bolyai's solution. It's a solution that was brought out by somebody called Poincaré around the end of the 19th century. Yeah, so we have progressed to be another some 60 years or 70 years since the discovery of Gauss, Bolyai, Lobachevsky, etc., etc. Person who really made hyperbolic geometry run into something which is very active today is Poincaré, and this is something that was given by him. Okay, all right. One way you can think of this, one motivation for this comes from complex analysis. So since many of you are all of you familiar with complex analysis? Yes? Okay. So then the thing is, this is the geometry. The complex thing is that, so you look at the complex plane. If you have, say, the disk or the ball, yeah, inside the complex plane, yeah, the unit disk, mod z less than 1, or any other nice such convex domain, yeah, proper convex subdomain of the complex plane, yeah, that has a naturally associated geometry. It's something called the uniformization theorem. So from analysis it goes to geometry, that's called uniformization. Yeah. So this was proven around Poincaré, Koebe, Klein. This was around the end of the 19th century. That's when it came up. And the connection between the analysis, the complex analysis, and the geometry was discovered by these guys. Yeah? That's where this metric really comes up. Okay? So it really comes from complex analysis, not from real analysis. Okay. So that's this other story. Fair enough. So this is the answer. So once you are given the answer, now what do we have to do? What we have to do is find out what the straight lines in this geometry are. Once you have found out what all the straight lines in this geometry are, given a straight line, given a point lying outside that straight line, how many straight lines are there, how many geodesics are there through that point, not meeting the first one. That's all that we have to do. Which means what? The whole thing now boils down to what are the straight lines in this geometry. That's all we have to do now. Yeah? But we are given a formula, so we'll have to compute what the geodesics in this geometry are. So the first thing is that vertical straight lines in the upper half plane, so also called the hyperbolic plane, these are geodesics. Vertical lines are geodesics. I have not said anything about horizontal lines. Yeah? If the vertical and the horizontal guys were geodesics, we'd essentially get back Euclidean geometry. Yeah? So one is being very careful here. Only the vertical lines are geodesics. It turns out that the horizontal lines are not. They are very far from geodesics. In fact, the vertical segment between 2 points is the unique straight line joining these 2 points. Okay? How do we prove this? So take a point, take a smooth path. Okay? So now this is on some vertical. Yeah? 0, y1, 0, y2. They are joined by a smooth path, sigma. Okay? So sigma of this is given by some x of t, y of t. Yeah? What's the length? It's going to be dx square plus dy square by y, because now the metric is dx square plus dy square by y square. If you take the square root, it becomes dx square plus dy square by y. Correct? But dx square is going to be always locally, it's going to be some function squared, right? So you reduce that, you throw out that positive term, that's going to be always greater than or equal to dy by y. Yeah? And dy by y, you know the integral is log y2 by y1. Correct? When will that inequality, so the shortest paths will be realized precisely when dx is identically 0. Correct? Which means what? Yes, yes, yes. X is constant. Yeah? Which means what? So x coordinate is constant means it's a vertical line. That's exactly that statement. So we have proved essentially that the vertical straight lines are geodesics and that they are the unique guys. I mean, if and only if, this is an if and only if statement. Yeah? So the only guy which minimizes the shortest distance between 2 points is the vertical, provided those 2 points lie in the same vertical line. Okay. Alright. Now we want to, so we got one collection of straight lines, yeah, the vertical lines. The next thing is, we want to produce new guys, new geodesics. Okay? First thing you note is that f of xy goes to x plus a comma y is also an isometry. Why? x1 is now equal to x plus a, y1 is equal to y. So dx1 is equal to d of x plus a, which is equal to dx. Right? So square root, so the metric form dx square plus dy square by y square is equal to dx1 square plus dy1 square by y1 square. So this is an isometry. It preserves the infinitesimal form of the metric. Yeah? And therefore, if you take the vertical line x is equal to 0 and you translate it to x equal to some constant, you're going to get new geodesics, which means what? All the vertical lines are geodesics. Something that we knew from before, but there's a different way of seeing it. Now we come to another kind of transformation which was known from the time of Fermat. Okay? Something called this spherical mirrors. Yeah? So if you have, when we do optics, geometric optics in school, you use mirrors, right? What if you use spherical mirrors? These are also things that are done. Yeah? So if you have so what you get is, mathematically what you get is essentially what is called an inversion in a semicircle. So what's an inversion in a semicircle? Define the map from the upper half plane to itself by g of z is equal to r square by z bar. What does that mean? So suppose capital R. So capital R, suppose it's 1 for the time being. Yeah? So which means what? You take a semicircular mirror, yeah, of radius 1, center 0 on the upper half plane. Okay? So semicircle centered at the origin, 0, 0. Radius exactly equal to 1. Yeah? Suppose that semicircle is now a mirror. Yeah? So suppose you have now some point at coordinate r, theta. Yeah? If you reflect that r, theta in the mirror, where will you come to? Really? It's only in the upper half plane, yeah? So you have this semicircle here, yeah? And the reflector, the surface of the semicircle is a reflector, yeah? And r theta is here. How can we, you are taking polar coordinates, right? So r, theta, r is always positive. So where will it go to? So just, don't calculate. So suppose you have a reflection. So it is going to reflect when the ray from the origin hits the mirror at right angles. Yeah? So if you reflect, it's going to come inside the semicircle. Right? It's going to come inside the semicircle. So basically, theta, the angle, the polar angle, the angle coordinate theta is going to remain constant. So r, theta is going to go to something on that same line, but theta will be remaining constant. Turns out, this you can calculate. This is geometric optics. Nothing more than school geometry required here. R going to 1 by r is the exact point. So if it reflects inside the mirror, it will go to 1 by r. If the sphere had radius capital R, is going to go to capital R square by little r. Yeah? If you want to write it in complex coordinates, is z is little r, theta, r square divided by little r. If you write e power I theta, you are going to get e power minus I theta at the top. Yeah, so you don't want to get that, you want to get e power I theta at the top. So the formula is given by gz equal to r square by z bar, the complex one. Yeah? Reflection switches the orientation of the plane. Yeah? So you can't expect a z there, you should have a z bar. So this is all, sanity checks are there. Okay? So it goes to r square by z bar. Okay? Here's the next basic statement. Inversions. So this G, inversion about a semicircle, is also an isometry. Okay? So the first thing was that vertical translations in the horizontal direction, x goes to x plus a comma y is an isometry. The next thing is that these spherical inversions are also isometries. Okay? Inversions in semicircles centered at the origin are isometries. I'll prove this. Little bit of complex analysis. Once we are done, suppose we have proven the second statement. Yeah? The next thing is that the image of a geodesic, this is something I've already said, the image of a geodesic under an isometry is another geodesic. In particular, the vertical straight lines which we already had, their reflections, their inversions under, their images under these inversions will also be geodesics. So we are going to get new geodesics in the process. Okay? And here's, I'll tell, in fact, you are going to get all geodesics in the plane in this way. Okay? So we don't have to do too much more. We just have to prove that first, the inversion in a semicircle is an isometry. 1. Step 2, compute what the image of the vertical line is after inversion. Okay? This is what. Okay? So, now we start doing a little bit of computation. What do we have to do? We have this nice formula, z goes to r square by z bar. Yeah? For simplicity, let us say z goes to 1 by z bar, capital R is equal to 1. Yeah? Now we want to compute. So, what do we want to compute? We want to compute that this formula dx square plus dy square by y square remains invariant under this transformation. Yeah? Use complex coordinates, dx plus I dy is equal to dz. Yeah? Then, now instead of x and y coordinates, we are changing to independent coordinates z and z bar. Okay? A complex coordinate and its conjugate. So dz bar is going to be equal to dx minus I dy. So what is dx square plus dy square by y square in complex coordinates? That's just minus 4 dz bar. What is dz bar? dz bar is exactly equal to dx square plus dy square. Right? dx plus I dy, dx minus I dy. Multiply, you're going to get dx square plus I dy square. and y is equal to z minus z bar divided by 2i. Yeah, x plus iy minus x minus iy, which is becomes 2 times I times y, you divide by 2i. But there's a square, so 2i times square becomes 4, so you take that 4 to the numerator. So this minus 4 dz bar by z minus z bar whole square is rewriting the hyperbolic metric, but now in complex quantities. And what we have to do? Under this transformation, what happens? R theta goes to 1 by r comma theta. Yeah, I'm just taking capital R is equal to 1. Yeah? So, z goes to 1 by z bar. That's my transformation, simple transformation. R comma theta goes to 1 by r theta, means z goes to 1 by z bar. What does z bar go to? 1 by z bar bar, which is 1 by z. Okay? So then what does dz go to? Minus 1 by z bar square dz bar. What does dz go to? Dz bar go to 1 minus 1 by z square dz. Put all this back into this little formula there. Hence, inversion. So you just take all this stuff, put it back. Dz now goes to replace this on the left side, replace dz by minus 1 by z bar square dz bar. Replace dz bar by minus 1 by z square dz. Yeah? In the denominator, replace z by 1 by z bar, replace z bar by 1 by z. Yeah? What happens? You get z bar minus z by z bar in the denominator squared. So you get 1 by z bar squared. That means 1 by z square, 1 by z bar square. Yeah? In the denominator of the denominator. Right? What is the denominator of the numerator? Just look at that. It's minus 1 by z bar square times minus 1 by z square. What is that? Again, 1 by z square, z bar square. So that stuff cancels off. So where z goes to 1 by z bar gives you an isometry. Okay? So this is half a page of 5 or 6 lines of computation is all you require to establish that inversion in a semicircle of length 1, of radius 1 is an isometry. Yeah? Do the same computation with z goes to some positive number by z bar. Same thing works, and you get that inversion in any semicircle is centered at the origin is an isometry. Yeah? But the origin is something that we chose at random. Translation in the horizontal direction is also an isometry, which means I can shift the origin to any other point on the real line, which means inversion in semicircles centered on the real line. All of these guys are isometry. So we get a huge collection of isometry. What do we want to do now? Take this vertical guy and invert it in this semicircle, in one of these semicircles. Okay? That will give us new geodesics. Okay? So given a straight line, where are we going to invert it? So basically, you want to, so if you invert it on a semicircle has, on the real axis, it has two or three distinguished points. It has its center, but if you have a vertical line going through the center and you reflect, that vertical line is going to come to itself. With the opposite orientation, it is going to come to itself. The next natural point is the point of tangency. So let's try to look at that point of tangency. So you have this vertical guy, yeah? Okay? So this vertical guy, where does it go to? Yeah? And now we are again in the domain of Euclidean geometry. R comma theta goes to 1 by r comma theta. Yeah? And here's the answer. So you take this big semicircle, yeah, passing through D, yeah, tangent to your vertical line. And that little semicircle there is the image of that vertical line under inversion about this big semicircle. That's the claim. Okay? Now, why would you expect that? That fellow is tangential to the semicircle on the real axis. Yeah? This vertical line is tangential to the semicircle at this point. Yeah? As you go off to infinity, r comma theta, so assume that little a is actually your origin. Okay? What do we want to prove? So what do we have to prove? So you take this. So the guess is that the semicircle is a guess. Yeah? Why? Because that's the most natural curve which joins this point to that point and stays inside this big semicircle. Okay? So now what do we do? So what we have to prove? You take this semicircle, this is your origin, take B, take C. Yeah? C is given by, let us say, r comma theta. And what do we want to prove? We want to prove that the coordinate of B is 1 by r comma theta then. We know that r comma theta goes to 1 by r comma theta. We are now wanting to see that same formula geometrically. Yeah? Which means essentially that this guy, if the distance AC is r, then AB must be 1 by r. Right? Or in the general case, capital R square by r. Right? Which means what? AB times AC must be equal to capital R square. The denominator is something, the numerator is something. Multiply the, so AB times AC must be equal to the radius square. That's what we want to prove. Yeah? Little r and then capital R square by r, multiply them, you expect to get r square by r into little r is equal to capital R square. Yeah? So what we want to prove? We want to prove a Euclidean geometry problem. AB times AC equal to AD square. That's what we want to prove. That's all we want to prove, nothing else. Yeah? I don't think I've drawn the similar triangle. Let me just see the next slide. Oh. So, how do we prove this? So let's do this construction. Take B, join it here. Yeah? So we'll call this point E. Okay? A times D is equal to A times E. Correct? It's a radius. Right? So what do we want to prove? AB times AC equal to AE squared. But once you've joined this point to this, then you get a right angle here. It's the angle subtended by the diameter inside a semicircle. So then the triangle ABE and the triangle ACE are similar triangles. Okay? So once you have this basic class 8 level geometry, that Euclidean geometry that we are doing, what do you get? AB times AC equal to AD square. That's basically what you get. If you have AB, that's the angle opposite this side. It's the side opposite angle AEB. But this angle AEB is equal to the angle ACE. Right? In the similar triangle thing. So that means AB divided by AE is equal to what? Take the side opposite the right angle. It's AC divided by, no, it's AE divided by AC. Yeah? So AE times AE is equal to AB times AC. Okay? That's a computation using similar triangles. Okay? Which means what? Which means the image, this one simple Euclidean geometry thing tells you that this vertical line inverted gives you this semicircle, this smaller semicircle. Okay? What property does the semicircle have? It's a semicircle again centered on the real line. Yeah? Meeting the real. I mean that the entire property is that this new semicircle is again a semicircle which is centered, whose center is on the real axis. Yeah? Now, let us reverse engineer this construction. Claim any semicircle centered on the real line is a geodesic. How do we do that? So what do we want to prove? I want to prove that this semicircle is actually a geodesic. Yeah? Because we had started with this vertical line, we know that it's an image of that vertical line under an inversion, and therefore it's a geodesic. Yeah? Suppose we did not know that. Yeah? So suppose we did not know that this semicircle came from this kind of an inversion. What are we going to do? Take this semicircle, take one endpoint as a center of a larger semicircle, draw this larger semicircle now. Yeah? And from this point, draw a vertical guide tangential to the big semicircle and the small semicircle. Then, our previous computation says that this vertical line inverted about this big semicircle, which we have now constructed, is not given to us now. Yeah? Constructed, so you invert it, you get your original semicircle back. That means any semicircle you start off with centered on the real line is a geodesic. Yeah? Okay? So, yeah, if you have any questions, you can feel free to ask. Go ahead. Puche. Yeah? look, at worst you are going to be wrong, yeah. Nobody is going to put you in jail for being wrong in a maths class. Ask whatever question you have. हाँ जी, बिल्कुल. अरे हाँ भाई, तो जियोडेसिक मैंने बताया कि स्ट्रेट लाइन जियोडेसिक थी. हाँ, मैंने थोड़ा ही ना बताया कि सब जियोडेसिक स्ट्रेट लाइन है. ठीक है, वही तो मैं कर रहा था कि भाई सारे के सारे जियोडेसिक कौन है, यही तो निकालना है ना. ठीक है, तो मैं पहले क्या प्रूफ किया कि वर्टिकल स्ट्रेट लाइन, उसीलिए कई बार मैं बताया आपको कि वर्टिकल स्ट्रेट लाइन आर जियोडेसिक्स. बाकी जियोडेसिक कहां गए, गायब हो गए क्या? हाँ, बाकी जियोडेसिक कौन है, ये भी ढूंढ के निकाल रहे हैं. Okay. So, as a result, we have in the hyperbolic plane vertical straight lines and semicircular arcs with centers on the real axis are geodesics. बात बड़ी सीधी सी है. ये जो मॉडल हम निकाले हैं ना, dx square plus dy square by y square, ये एक हाइपरबॉलिक प्लेन का मॉडल है बस. ठीक है, तो उसके अंदर कोई अगर रहता, सोचिए कोई चीटी वहां रहता है वो हाइपरबॉलिक प्लेन में, उसके लिए ये स्ट्रेट लाइन और सेमी सर्कल में कुछ फर्क नहीं दिखेगा. हम बाहर हैं, इसलिए हमको लग रहा है कि ये यहाँ स्ट्रेट लाइन है और यहाँ सेमी सर्कल है. अगर कोई वही मैट्रिक के अंदर रहता, हाँ, उसको लगता है कि ये तो हम सीधा जा रहे हैं. ठीक, यही बात. वी आर ट्राइंग टू सी द हाइपरबॉलिक ज्योमेट्री फ्रॉम अ यूक्लिडियन पर्सपेक्टिव. अरे हमारा दिमाग सड़ा हुआ है, इसलिए हम कर रहे हैं. समझे? Okay. So, if we lived in a hyperbolic plane, these fellows we would call those guys straight lines, and these Euclidean fellows we would call them, okay, so these are some distorted fellows. Okay. Perspective की बात. Okay, so the semicircular arcs with center on the real axis are geodesics. ठीक है? तो अभी क्या करना पड़ेगा फिर आपको? What do you want to find out? So now we have established that semicircles with centers on the real line are geodesics. Original प्रश्न क्या था? Given a straight line. So let us choose. Go back to that picture. So suppose you have, सोचिए यहां हम एक parallel line खींचें. This is our line L. ठीक है? And now you have this new point C. ठीक है? How many lines? So let us, so there's some imaginary line going here. ठीक है? सोचिए ये वाला जो vertical line यहाँ है, हाँ, border जो है, वो एक, this is our given line. ठीक है? Given point is C. ठीक है? How many geodesics in the hyperbolic plane are there through the point C which are parallel to the wall, huh? To the boundary of this, to this vertical end of the screen. हाँ जी, कैसे वन हो गए? Now हम तो अभी बहुत सारे geodesic निकाले हैं ना. All the semicircles centered on the real line passing through C, which are disjoint from this boundary, are also parallel to it. एक तो दिख ही रहा है, the vertical line is a geodesic. ठीक है? बाकी और कोई है या नहीं है? कैसे कंस्ट्रक्ट करेंगे? How are we going to construct a semicircle passing through C, yeah, and not meeting this guy? If we can construct a semicircle centered on the real line, passing through C, not meeting this guy, then we would have a new example. A new straight line, which will be new geodesic, which passes through C but does not meet this vertical guy. कैसे करेंगे? अरे भाई यहाँ तो है ना, तो सोचिए, just pick some point at random. वही A को ही fix करते हैं, ठीक है? Take AC, take the perpendicular bisector, ऐसे करके यहाँ आ गया, यहाँ आपका सेंटर आ गया, ठीक है? So what will be the semicircle centered at this point passing through A? Because it is a perpendicular bisector, it will pass through A and C, है ना? तो यहाँ करके ऐसे आप एक बड़ा सा सेमीसर्कल खींच दिए. So basically what you do, take any point between this and this. Take any point. Join that point to C. Take the perpendicular bisector. See where that perpendicular bisector hits the real axis. Take that point as the center. And that point comma C as the radius. Draw the semicircle. It's going to hit C and the original point that you started off with. Okay? There is going to be a semicircle centered on the real axis. Hence a geodesic. Passing through C, not meeting the boundary of the screen. Okay? How many of them are there? For every point between this point and this point, there is a point. There is a line. There is a semicircle. है ना? तो ये इंटरवल का इसका कार्डिनलिटी कहता है. Cardinality uncountable होता है. For those of you who know. So you get uncountably many lines. So from one you don't get infinitely many. Not just infinitely many. You have a real lines worth of real line segments worth of lines passing through this guy. तो यही आखिरी स्टेटमेंट है. Theorem 4. In the hyperbolic plane H, vertical straight lines and semicircular arcs with center on the real axis are geodesics. Hence we have the new parallel postulate. Given a geodesic L and a point X on H, hyperbolic plane, lying outside L, there exists infinitely many by infinite geodesics L prime lying on the plane. अभी उसका नाम बदल गया. ठीक है, प्लेन पहले था P, अभी हम कहते हैं उसको H. सिर्फ उसका नाम बदल दिया. Passing through X and parallel. Parallel to L means not me. ठीक है? So, which means what? Again, what is the set of axioms there? First four axioms, ठीक है? Last वाला क्या? There is one and only one line था. अभी यहाँ क्या हो गया? There are infinitely many lines हो गए. तो one और infinitely many तो समान नहीं है. One and only one and infinitely many are certainly not the same. ठीक है? तो ये जो fifth postulate है, ये बाकी सारे चार axioms के साथ consistent है. One and only one is also consistent with the first four. ठीक है? So, as a result, what is the conclusion? It basically says that Euclid's problem is not the right problem to approach. The correct thing to say is that the first four axioms and the fifth postulate are consistent, and the first four axioms and the negation of the fifth postulate are also consistent.